Hey guys, today we are looking at 6.2's notes, which is all about compound interest and then some growth and decay problems, specifically looking at different real world applications of our exponentials. So compound interest is something that we talked about back in Algebra 1. It is one thing of the topics that we talk about, it is one thing that has huge applications for everyone, regardless of what you choose to go into for your given field, because compound interest is how interest is calculated. It's used in your savings account, with your credit cards, with student loans, mortgages, all of that stuff that you're either charged interest or you earn interest on uses this compound interest formula. And in this formula, we've got a lot of different variables happening. We've got a lot of different things to keep track of. So when we're looking at this, our equation uses some different variables than we're used to. Usually we're just using x and y's, but here, because we have so many different aspects to this that we have to account for, we use some different variables to stand for what we're looking at. So our a value here in the equation, that's the total balance in the account, which I use the account here just because usually when we're doing compound interest problems, it's dealing with dollar amounts. So amount in the account is our a value, that's at the end. The principal is my starting value. So this capital P here, that's my principal investment. It could be how much you're putting into the savings account at first. It's how much you take your loan out for. That's your principal starting value. My R in my equation is my annual interest rate. Now that is given in decimal form in the equation. And we can sometimes be given it as a percentage for what we're given. So just make sure you remember, if you're trying to convert from a percentage to a decimal, like if you're trying to figure out what to plug into your formula, when you have like 35% that you're starting with, to move that into a decimal, you just move your decimal place 2 spots to the left. To the left. Or vice versa. If you're given the percentage in your equation and you're trying to figure out what it is as a percent instead of as a decimal, you would just move it 2 spots to the right. The last two pieces here, N and T. N stands for the number of times we compound interest per year, and then T is our time variable. That's like our X value. That's T number of years. So N is something we'll look at different ways of compounding interest. It's basically just talking about how many times a year we check the account, calculate the interest, and then put that money back into the account. So for this first example, just to use a straightforward one, we're starting with an account balance of $100, and we're going to leave it in there for 20 years. We know that the account pays 1.2% interest, and it's compounded twice a month. So just going through our variables, the things that we're looking for, we've got the nice kind of acronym print, PRNT. We're looking for our principal, our rate, our number of compoundings, and then our time period. So if you need to go through and label each of these individually, feel free to do so. As you start getting better at them, you're not going to have to really do that for each individual problem that you're working with. You'll be able to just kind of take the information out of what we're given and plug it right into the formula. But for the sake of this first one, let's go ahead and label what each of those things are. So P being my principal, that's how much we're investing. That's our initial amount that we're putting into our savings account here. R is our interest rate, but remember we have to put that in as a decimal. So even though this percentage that I'm given is a decimal, 1.2%, because it's a percentage, that's not in decimal form. We still have to move that decimal spot 2 to the left. So 0.012 is what we should be using for my R value. My N is my number of compoundings per year. So this is how many times a year we are going to calculate that interest. Now in this one, we're told that it is happening twice a month, and we can't just put 2 in there for N. Remember, N is how many times per year we're calculating the interest. So if it happens twice a month, that would be 24 times throughout the entire year. And then last but not least, our T value, that's our number of years, that's our time that it's staying in the account, and that one we're given that it's going to be in there for 20 years. So as we go ahead and put in our different values into our equation, that's supposed to be our amount in the account is equal to 100 times 1 plus 0.012 over 24 to the 24 times 20th power. Now with this, you can use your calculator and just plug this in directly. You're just going to need to make sure you use enough parentheses, because we have to make sure we're doing this in the correct order, following order of operations, with our exponents happening first, and then simplifying what's inside our parentheses, followed by multiplication, dividing, adding, and subtracting. So here, the way that I would do this, I do these first two steps just kind of separately, just to make sure I do them. So inside my parenthesis, I'm going to simplify this. 0.012 divided by 24 ends up giving me 0.0005, and then I add 1 to it. So in my parenthesis, ends up simplifying down to just that, 1.005. Sorry, 1.0005. And then my exponent, my 24 times my 20, gives me 480. Because now you should be able to type this directly into the calculator as it is. 1.0005 to the 480th power, and then multiplied by 100 afterwards, and we should get a total of $127.12. Making sure we round, obviously, to the nearest 2 decimal places, since that is to the nearest cent, since we're doing dollars here. So next, for example B, we're going to take a look at how that compounding rate impacts how much money I make. So in this problem, we're comparing these two different options, these two different values. We're starting with the same investment, $350,000. We're given the same interest rate. We're earning 5% over the year, and we're going to leave it in there for the same amount of time, 10 years. It's just that we're going to be compounding interest more often or less often, depending on which of these two options we're dealing with. So it's going to be the same investment, the same percentage. We're still gaining 5% over the course of the year. We're still leaving it in there for the same amount of time, but we're going to see how this impacts it. Now, these two are described to us a little bit differently. I think the monthly one is a little easier for us to see. That's just going to be 12 times a year. If our interest is compounded monthly, that's just once every month. So that's 12 times during the year. Quarterly is a little bit different. You can probably guess what that means. Quarterly, in the kind of the financial world, they have different quarters of the year split up, the entire calendar year, just like we have a school year split up into 4 quarters. They have just divided into Q1 through Q4. So quarter 1 is the first 3 months of the year. Quarter 2 is the 4th through the 6th month, and you can kind of see how it splits up from there. It's just taking the year and dividing it up into 4 groups. So each group, each quarter ends up being 3 months long. So the way that my equations and my formulas will be set up here, my P times 1 plus R over N to the N times T power. My initial investment is $350,000 times 1 plus 0.05 over, in this case, quarterly is 4 to the 4 times 10 power. And then over on the monthly side, basically the same thing, it's just that our 4 is going to become a 12. So 350, 3,000, 1 plus 0.05 over 12 to the 12 times 10th power. So if you go through and use your calculator, again, the same thing I would suggest. I would do this 0.05 divided by 4, add that to 1, and then we're going to be raising that to the 40th power. So over here on the quarterly side, we should end up with a final value after that 10 years of $575,266.81. And then on the monthly side, you should end up with $576,453.32. So you can see, without changing how much money we're putting into the account, without changing the percentage rate, we're still gaining 5% every year, and we're leaving it in there for the same amount of time. We're making over $1,000 more just by compounding that interest more often. So that kind of leads into the next part, is if we can calculate our interest more often to gain value more quickly, what's the fastest that we can do that at? What's the best rate that we could possibly get by compounding it as often as possible, which gets into continuous compounding. So this is a hypothetical thing in the financial world. You're never going to get something that compounds your interest continuously, because no financial institution would ever give you an interest rate or a savings account that compounds continuously. It means that every single instant, they're taking the account balance, giving you your interest rate, putting that money back into your account, and then continuously just doing that. They keep calculating your interest and applying it immediately to be able to calculate what that interest is. Now, this is seen more so kind of in the scientific world. When we're talking about continuous growth rates, usually bacteria or other things that grow naturally, they don't just like wait and like they don't stop growing or start growing every day or every week. That growth happens, that population growth is happening continuously. So that's where this is applied, but we can still kind of put this continuous interest kind of veil to our financial problems and kind of deal with it in the same way. The way that our equation changes, my variables here all mean the same thing, except that this E, this is a constant value. E is, I think it's 2.78 something. I don't know off the top of my head because it's not something I use all the time. But it's kind of like pi, where pi is, we know it's 3.14159265 and on into infinity. It is an irrational number. It is never ending. It is never repeating. E is kind of the same thing. It is some really, really smart dead dude back in the day figured out that if you continuously compound your interest, if you're looking at continuous growth rates of populations, they figured out that this is the rate at which you would have to use in order to get that. So it's a number that we'll just use. There's a button on your calculator, just like there's a pi button on your calculator that we'll use for the natural number E. And it's something we'll discuss moving forward. We'll get into in the next section. We start talking about logarithms. We have different bases, and base E, natural log, is something that we'll utilize. But the important thing here is to know that E is just a constant. It's just a number that you guys will use. P, R, and T, and A all still mean the same thing. P is still your principal investment, R is still your growth rate, and then T is still the time period. So, for example, see here, Joan was born and her parents deposited $2,000 into a savings account, paying 4% interest, compounded continuously. We're trying to figure out when she turns 15, how much money is she going to have in her account? If she's starting to look at colleges now in her freshman year, how much money has she got to work with? So in this problem, again, I'm just going to plug in stuff we know. My principal investment is that $2,000 times E to the, our growth rate is 0.04 when we put that into a decimal, times 15th power. So in this, your calculator will have it listed a couple of different ways. I'm just going to do this quick multiplication here. 2,000 E to the, this is going to end up being 0.06, sorry, 0.6, not 0.06. 0.04 times 15 is 0.6. So on your calculator, it could look a couple of different ways. Some calculators have a button that looks like this when you type it in. There's an E button on your calculator. It'll pop up like this. If that's like if you're using calculators similar to what I have in my classroom, like the TI-30X2s, if you're using like a TI-83 or an 84, when you hit the E button, it'll kind of pop up like this, and like it gives you the little box for what you want to pick for the exponent. Either way, you should be able to do it that way. Some basic calculators, like if you're using your phone calculator, there's an E button, and it'll probably even just like put in what the number is, 2.78 something, and then you can still raise it to a certain power that you want. So here we would do E to the 0.6 power, and then multiply by 2,000. So we should be able to see that in this case, we end up with $3,644.24. So on a 4% interest is pretty good, but just after 15 years, without messing with it or doing anything else, we've we're pretty close to already doubling our money. So you can see really how powerful and how impactful that continuously compounding interest is, which is why no banks will ever give it to you, because that would be too good for us. Okay, so flip it on over to the backside here. We're getting into some more basic exponential growth and decay problems. In the last section on Thursday and Friday from last week, we looked at how exponential functions can be in either one of two forms. It's either exponential growth, and we know that that happens when my base b is greater than 1, or it could be decay, where your base b is between 0 and 1. And so we're going to be looking at those two different examples. So this equation is something more close to what we're used to seeing. This y equals a times b to the x power, using our kind of more standard variables. Here, a still represents your initial amount. My base b is my growth or decay factor, and then my x and my y values can mean it could be a whole different things depending on the frame of which we're given our problem. X could be time, it could be our number of trials or iterations, but then our y value is going to be still our final amount. So if we jump into a kind of a basic example here, for example D, we're reading a novel in which our entire 40-player baseball team becomes zombies. It is predicted that the number of zombies will triple each day. How many zombies will there be after a week? So after 7 days. So the numbers that we're given here, we've got 40 players. We are told that they're going to triple each day, and we're trying to figure out how many zombies there are going to be after a week. So I'm going to start off by just writing our basic equation here. Our 40, that's going to be our initial amount. That's how many players we're starting with. So that's going to be our A value. Our B, our growth or decay factor, is going to be 3, because we're told that our number of zombies are tripling every day. They bite 3 people, and on others 3 times as many as there were the previous day. So our generic formula, still with x and y in here, would be 40 times 3 to the x power. That would be the generic formula for the situation that we're trying to describe here. And then if we're trying to evaluate how many zombies there's going to be after a week, we would just replace x with 7. So 3 to the 7th power times 40, which 3 to the 7th power is 2,187. So if we multiply that, we would end up with 87,480 zombies. There we go. Lots of zombies. So that one's pretty straightforward. Those ones seem pretty easy because our base, our variable b, was a nice whole number, right? It's a clean thing, so that makes it easy, which is not usually the case. We know that life is very rarely that nice and pretty. We're going to have to be dealing with some ugly stuff, so let's take a look at what happens when that is the case. Most of the time, similar to what we're working on in the front side of the notes here, we're going to be dealing with some kind of percentage change, where we're increasing or decreasing by a certain percent. And when that is the case, this is more what our equation would look like. So we're going back to those kind of variables in that setup that we saw on the front side, except that here, these our equations are obviously format-wise a little bit different. We have P still being my principal investment, A is still my final amount, R is still my percentage rate, my rate of change, and then T is still that time period. Except that now, my base is just 1 minus r for a decay problem because we're losing a percent of the value. And then in my growth problem that we'll see down below with example E, we're gaining a percent, so it's going to be 1 plus our r value. Otherwise, it's still my base to the t power times my initial amount. So in example E here, we bought a used car for $18,000, which that's a pretty nice used car, probably only a year or two old. Maybe it was just a lease, and now we're buying it for $18,000. We know that in general, cars are going to lose value as they get older because of something called depreciation. The car depreciates or loses value as it gets older. There's newer cars that replace it. Wear and tear on the vehicle, the more miles you have, cars just depreciate. In general, cars depreciate around 12% a year, so that's what we're going to assume for this problem, 12% depreciation rate. we're asked to write an exponential decay model that represents the situation, and then use that to estimate the value of the car after 8 years. So, looking for our 3 variables, we need P, R, and T. So we have our principal investment, that's that $18,000 that we started with. Our R is 12% per year. That's the R value there. We're going to have to make sure we convert that into a decimal. And then the last thing that we'll plug in there is our T value. That's our time period. That's going to be 8 years. So here they want us to first write the equation of the model. So A equals 18,000 times, that's 1,800. 18,000 times 1 minus 0.12 to the T power, which that should be rewritten. We shouldn't leave it like that. 0.88 to the T power. That would be my first answer. That's the generic model. And then for actually evaluating how much our car would be worth after 8 years, 18,000 times 0.88 to the 8th power. So we'll go ahead and use our calculator, 0.88 to the 8th power, and then multiply it times 18,000. And that final value of our car after 8 years is now only $6,473.42. So that would be the value after that time period. That's just with a 12% decay. All right, last but not least, example number F here, number F, letter F, example F. We've got a train that is traveling downhill at 140 miles an hour. Suddenly the brake system fails and the train continues picking up speed, getting 11% faster every minute. We're asked to find how fast the train would be going in 5 minutes. So once again, we'll go ahead and just write the generic equation first. 140, that's going to be that starting speed. 11% is going to be our rate that we're changing at, and then it tells us that we're traveling for 5 minutes. Now, it's important to note here where it has my 11%, that says that we're gaining 11% per minute, every minute. So that's my T value. My time value has to be in that same unit as what it tells me for my percentage change. On that previous one, it tells us that we're losing 12% of the value every year, which is why my T value should match that time period. So for our generic equation here, our A, which I'm going to switch it up. I'm just going to do it because I want to. S for what our speed is for the train is going to be 140 times 1 plus 0.11 to the T power. Because again, 11% as a decimal would be 0.11. We should move that decimal place 2 spots to the left. So our equation for the speed of my train is 140 times 1.11 to the T power. And that's my generic equation. I know they didn't ask for it explicitly, but I want to do that anyway. And then for the last part here, I'm going to actually plug in 5 for my T value. So the speed of my train should be 140 times 1.11 to the 5th power. And we should get that after 5 minutes of being out of control, that's a $sign, not an S, we should end up with a train going 535.91 miles per hour. Now in this one, I didn't specify how to round it, and if I don't specify, just assume that you should be rounding it to 2 decimal places. 2 decimal places. So, that is all I have for you guys for today. Your homework is down there at the bottom right corner, page 301, 37 through 44 all. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day, and we'll see you soon.